Yes. Please be quiet. So we'll just review what we have done. We have started with linear regression and the regularization on linear regression, and then we have seen how to use the similar regression framework for classification. Okay, where your end goal, please be quiet. In 2 minutes, you have to settle down, please. The laptops and mobile phones are not allowed. Fine. So we have we have formulated our regression framework, and we have seen the regularization on top of the regression, and we have also seen how to use a simple linear model or the similar setting like our regression setting. Can we use it for classification? So that we have seen in our least squares for classification, and later we have discussed the concept of bias variance trade-off. In bias variance trade-off, our main goal is to decompose the test error into 3 terms, and these 3 terms have their own significance. Okay, basically your variance term will actually convey you some information about overfitting, and your bias term will convey about your underfitting, whether the training error is high or not, and the noise is coming from your data set itself. So we have seen the motivation behind these 3 terms and how to decompose your test error into these 3 terms. Okay, we have seen the derivation also. And we have seen some visual examples yesterday. So in case if you have not attended or if you are not following, we can review this in your tutorial session. You can just post your questions, we can discuss. Okay. And yeah, and also we compared our bias and variance with respect to complexity. So in the previous case, when we actually discussed overfitting and underfitting scenarios, we have just seen how test error and training error varies with respect to model complexity, right? So in the previous classes, we have just seen test error versus your complexity. Please be quiet. Test error versus complexity and training error versus complexity. So in the bias variance trade-off, instead of depending on your training error and testing error, you are computing two more different terms. In a way, they are similar to your training and testing error. So those terms are your bias and variance, and we have seen how they vary with respect to your complexity. Okay, so till now we have done this. So now let's come to our least square solution for classification. So we have seen this example, right, when we discussed our classification framework. Just a simple linear model for your classification. We have seen that when we added outliers, so this is the solution, or this is the hyperplane given by your linear model, which you train with your mean squared error. Okay, so if this is the linear model, so this one is your linear model. When you don't have your outliers, it is working fine. It is actually separating well. But when we have some outliers in a particular class, you can see that my hyperplane actually shifted. Okay, so we have actually concluded that my least square solution is not robust to outliers. Right? So that is coming from your basically training process itself. You have used mean squared error to fit the model. So it is directly the outlier presence is directly impacting your model fit. Right? So that's what we have seen in the least square solution. So now in your least square solution, if you see, you will have a linear model, which is the W parameter matrix, and into your input ideally should give you a predicted vector, right? Based on your K-class classification, you'll be getting the vector, and based on the maximum in your vector, you will conclude about your predicted class. That's what we do in your classification, right? I hope you have done the same in your assignment also. Yes? Right? So this is what is happening in the least squares. Now we are already saying that it is not robust to outliers, right? So the problem is coming from your mean squared error. Now the question is how to fix this. Can I fix my linear model so that I can fix this issue, or I can make this entire machine, classifier model robust to outliers. Okay, so the problem we have identified is because it is a mean squared error and we didn't interpret outputs as probabilities in our simple least square solution. There is no constraint, right? I didn't put any constraint that my output, predicted output coming from my linear model should be, or each predicted value coming out of my linear model should be between 0 and 1. That condition I didn't put when I am training my least square solution. So the reason is the outputs are not interpreted as probabilities, but your ground truth labels are one hot encoded vectors. So they are interpreted as probabilities, but your predictions are not. Right? So this is one of the reason, and the sum of your vectors it's not equals to 0 because these are not probabilities. Now, to my linear model, which I have already, which is giving out the predicted vector for me, but those are not probabilities. So because those are not probabilities, I am facing this issue in presence of outliers. Now, how can I give probability or probability how can I add or how can I modify my entire linear model so that outputs will be interpreted as probabilities? Okay, so that is the question we'll ask. Okay, you have your simple linear model giving out your vector for you. So how can you modify your linear model, simple linear model? Okay, this is predicted. You have your predicted into your. So how can I modify this linear model so that the outputs will be interpreted as probabilities? So do you have any solution for this? Can you think of any solution? Adding some function, yes, add a function. What kind of function do we need here? Adding a function is a solution, yes, but what kind of function? Which has range 0 to 1, okay. Then any other? Adding a function with a range between 0 to 1 definitely will solve this problem, right? Because I am saying that I want to interpret my outputs as probabilities. Okay, so now the answer is correct. We have to add a non-linear function after your linear model to modify your outputs to probabilities. Okay, so we have like two different cases. One is like k is equals to 2, where it is just binary classifier or binary classification problem, and where your k is greater than 2, that is your k class classification problem. So in your binary classification, you have a linear model and it is taking x and it is giving you some intermediate value, and to this you add a function called sigmoid for your binary classification. Okay, sigmoid is a nonlinear function and sigmoid's range is between 0 and 1. Okay, so this gives you the predicted probability. Suppose if this is your xi, this is your predicted probability, and this xi has the ground truth probability also. Okay, so this framework is called your logistic regression. Logistic regression is very simple. It is just a simple linear model plus your sigmoid. Okay, sigmoid is actually converting your predicted vector into probabilities in your binary classification problem. Now coming to your k-class classification. Okay, again you will have a w and you will give an xi, and here in this case you will get a vector, right? So this vector should go into a non-linear function. Can you guess what? Can you guess the function here? Just a softmax will work. So in your k-class classification, your nonlinear function is your softmax. Okay, just a simple linear model plus your softmax will give you k-class classification or k-class logistic regression. Okay, so this is also called your softmax regression. So let's see what are these softmax and sigmoid. You know the function for sigmoid, right? Sigmoid of x is defined as 1 by 1 plus e power minus x. This is a sigmoid function. Yes? Okay, so this is your sigmoid function. And sigmoid function at 0, it is 0.5, right? How will it look like? Like this maybe. Like as x is tending to infinity, like your sigmoid will go towards 1. And if it is going towards minus infinity, your sigmoid will tend to 0. Right? So this is your sigmoid function. So can you derive your sigmoid function and tell me the derivative of sigmoid function? Please write down and derive the derivative for sigmoid. So sigmoid's derivative is, can I say this? Did you get the same answer? Just start with your derivative, just apply derivative to your sigmoid function, and then if you expand, maybe you can try. I'll just wait for a minute. Did you derive the derivative? So the derivative for your this sigmoid function, like if you actually apply your derivation and expand, you will end up getting this term. Okay? Just e power minus x by 1 plus e power minus x whole square, and you can write these as two terms, and this second term you can write it as 1 minus 1 plus e power minus x. So this is nothing but sigmoid of x, 1 minus sigmoid of x. This is the derivative for your sigmoid. So the sigmoid function is a continuous differentiable function. Yes? Okay. So the derivative is clear, no? Fine. So let us define what is softmax. Suppose if you have a vector z, and like you have z12, like if it is a k-dimensional vector, if you apply your softmax, assume that you are getting your z hat, your softmax of zi is exponential of zi by summation I is equals to 1 to k exponential of So is this minus exponential or exponential of zi? Can you tell me what is softmax? Will there be a minus in exponential? No. This is the correct softmax, right? So softmax also a differentiable function, and it's a continuous differentiable function, right? So what is it doing? You have a vector of values. So after you apply your softmax, like each element after applying your softmax will be between 0 and 1. Do you agree with that? Because we have a normalization here, no? We have a normalization or a denominator term here. So because of that, after you apply your softmax, the output will have each component in your output will be between 0 and 1. And if you sum up all of these terms after softmax, they will sum up to 1, right? So these are like probabilities. So now in your softmax regression or K-class logistic regression, we will use softmax, and in your binary classification, we will use just sigmoid. Okay. Fine. So now we'll try to see how to learn a logistic regression model. So have you seen this already? Logistic regression? No? Yes? In data science 3, have you seen logistic regression? So you have a linear plus sigmoid. So you will be predicting of the probability and you will be giving an input. Okay. So maybe for deriving, right, just assume that your data set is simple one-dimensional data set, and your yi, which is your ground truth, it can be 0 or 1. Just assume that you are solving binary classification problem and your data set is one-dimensional. And your xi is just one-dimensional, okay, where d is equals to 1. Okay, fine. So this can be written as your output. Here I will just include your this is your linear model plus your sigmoid. Please be quiet. Then this will predict you the outputs. Okay, so this is your logistic regression model. So if I have to train my logistic regression model, it is nothing but training my W1 or getting the optimal parameters for my W0 and W1. Okay, so for this scenario, for the simple one-dimensional case and the binary classification, if I have to learn logistic regression, it is nothing but learning these parameters. Okay, so now can I use mean squared error to learn this? No, because I have the outputs are probabilities now, and the ground truth is anyway one hot encoded, or like it's anyway 0 and 1. You have class 1 and class 2. Okay, so now I will actually come up with the likelihood term here. To learn this model, I will come up with a likelihood model. Ideally, this likelihood should be maximum whenever my predicted label and my ground truth label matches. Okay, and those two are probabilities, right? And the likelihood term should be a minimum whenever they are not similar. Okay, so the likelihood, actually this is a kind of Bernoulli distribution. Pi is like a single probability and you have the another class, no? So this is like a Bernoulli probability only, right? You have 0 and 1. 0 and 1 possibilities. So in this case, likelihood term is written as, like you have, which is the predicted one, and you have the ground truth. Okay, so the other one is for ith sample I am writing. Okay, for a single sample, the likelihood term which will estimate the similarity between your predicted and your ground truth can be written like this. So let's see what happens to your likelihood term when we have all 4 possibilities. Okay, so the 4 possibilities are what? You are predicting 1, but your ground truth is 0, and you are predicting 0 and your ground truth is 1, and you have ground truth 1 and predicted 1, ground truth 1, and predicted 0 and ground truth 0. So for all of these combinations, can you find out likelihood and tell me the values? Using this formula, the likelihood formula for your Bernoulli distribution, can you find out the likelihood and tell me for all these 4 cases, what will happen to my likelihood with this formula? What will happen in 1, 0 case? Just substitute 1 in Pi and Yi as 0 and just tell me, no? Likelihood is 0 in the first case. Just substitute these values in your likelihood. I'm telling you that this likelihood is measuring the similarity between your predicted and your ground truth. Okay. So in this first case, what is my likelihood? 0. Second case, please be louder. 0. Okay. Because if you just substitute 0 power 1, it is what? 1 power 0. 0 into 0 anyway. So for 1 case, likelihood will be 1. Yes. And this case, likelihood is 1. Okay. So likelihood basically is maximizing, or like is maximum when both are similar, and when both are dissimilar, your likelihood is 0. Yes? Where? In third case, 1 minus 1 is 0. 0 power 0 is what? Not defined. See, 0 power 0 will assume it to be 1 here. Is it not true? 0 power 0 is not 1. Okay, let's go and find out what is 0 power 0. Okay. So what happened in these two cases? In these two cases, it is clear that you are getting zeros, right? So in these two cases, you are not sure what is 0 power 0. Just go and find out what is 0 power 0. Okay. So now here, this likelihood term, if I maximize, okay, then it means that I am making my predicted probability and my ground truth probability similar. Yes. So my learning my logistic regression problem boils down to maximize likelihood with respect to W1 and W0. Is this fine? See, this one you go and find out. You don't have to get stuck there. Okay. I have just defined the likelihood for a single sample, and I'm saying that I will learn my logistic regression model by maximizing the likelihood. Okay. So maximizing my likelihood, maybe I will write my likelihood in terms of W0 and W1, which are my parameters. And then for the entire samples, if I write, it becomes okay. So this one, if I apply log to this log likelihood, what will happen to my product? It will become summation, right? Okay. Sorry, I will have a log term here. Can you expand this and tell me? Can you expand the log and tell me the function? And also just apply, instead of log, apply negative log. And you expand this and tell me what is the output. Yes?
What's the logic behind using multiplication instead of addition in like?
What?
Why have we used multiplication instead of addition like normal summation?
See, here we will assume that each sample is an independent sample. IID, it's an IID distribution. So when both are independent, probabilities you need to multiply, right? P of x comma y is equals to P of x into P of y. So that's why we use product. Okay. So the product is basically coming with an assumption that your samples are IIDs, independently random, identical and independent samples. Okay. So can you expand this and tell me what happened? So this becomes log of pi power yi and minus summation I is equals to 1 to n log of 1 minus pi 1 minus yi. Okay. So this, if you expand, this log of pi power yi, right? Yi into log of pi minus summation I is equals to 1 to n 1 minus yi and log of 1 minus pi. So this is what? Minus log of L of, so this is your negative log likelihood. Have you seen this equation anywhere? Have you seen this equation anywhere? What is this equation? What is that equation? Is it entropy? It's binary cross entropy, right? So this is your binary cross entropy. Yes? This is your binary cross entropy. So this is equivalent to your so your aim was maximizing likelihood. This is equivalent to minimizing your negative log likelihood, and this is equivalent to your minimizing binary cross entropy. Do you agree with that? So now logistic regression is nothing but your simple binary classifier, and you actually formulated your training process with maximization of your likelihood. So this is the formulation that we have. This we wanted to maximize, and like if I actually apply log likelihood, then I will get this term, okay, this expansion. Instead of that, if I apply negative log likelihood, see, maximizing likelihood is equivalent to maximizing log likelihood, okay, and this is equivalent to minimizing your negative log likelihood, right? So negative log likelihood is nothing but your binary cross entropy. Yes? Fine. So now when you are training your logistic regression model, see, inside your logistic regression you just have linear and plus a sigmoid, that's it. It is not too complex. It is a very simple linear model with a sigmoid. But you are training this model by minimizing binary cross entropy. Okay, minimizing and learning your models, learning your parameters. It is equivalent to maximizing log likelihood. Okay, both are equivalent. Yes. So now if you want to train your logistic regression model, if you write your binary cross entropy and minimize your binary cross entropy with respect to your parameters, or maximize your log likelihood, both are same. You can use gradient ascent, like if you want to use this framework. You can use gradient descent if you want to use the first framework. Okay, is this fine? Okay, so now shall we derive what are the gradients for my, and actually if you ask me, this closed form solution for logistic regression, actually it becomes difficult because we have a sigmoid at the end. So it is actually very difficult because you have all log terms. So instead of going for a closed form solution, we will just use gradient descent or gradient ascent. Okay, gradient ascent on log likelihood or gradient descent on cross entropy. Fine? Is this fine? Okay, so now if I have to apply gradient ascent, okay, then what should I do? I should derive my gradient with respect to log likelihood. Yes, because maximizing log likelihood, I have to learn my logistic regression model. Yes or no? So if I have to do this, I have to compute this gradient. So shall we start finding the gradient? So what happens to this term? This is what, like I don't have minus here. It is simply yi log of pi plus Okay, so this is my log likelihood. If I just remove minus, this is my simply log likelihood. If I just keep negative sign here, it becomes cross entropy. That's it. Okay. So this term, what is my PI? PI is the output of my logistic regression, right? Yes. No. We will do it with both. Because when I am doing gradient ascent or descent, I will do one by one, no? Like I don't have a possibility or I don't have closed form solution for this. Okay. So logistic regression in general, you will train using your iterative method only. Okay. So now what is your predicted one? It is e power minus of w naught plus w1 into xi. Can I say this? You are getting the output from the linear model and then applying the sigmoid on top of this. So this is nothing but your sigmoid of w0 plus w1 into xi. Output of the linear model, sending it to sigmoid. That's it. So this is the output of my logistic regression. So can you substitute this expression in your, maybe in equation 1, this expression in equation 1, and can you expand? Okay. One minus yi into log of, in pi place I am just substituting this expression. 1 minus 1 by 1 plus e power w naught plus w1 xi. See, if we have to learn logistic regression, no, we can just learn in 2 sentences also. Logistic regression is simple, just a linear model with sigmoid, and just do gradient like iterative method to learn logistic regression. I mean, at this level also we can learn logistic regression. And if you can go deeper into logistic regression and you can derive each equation and see what is happening. Okay, so you have to be other side because you are all IITians and you are going to be engineers. So we should actually see what is happening inside. So that's why we are doing all of this math. Okay. So because whenever I write some math, no, I'll see why madam is writing all of this. That kind of expression I'll see. Fine. So this is fine. This equation is just your log of. Okay. So now each term I'll take out and we will try to derive dou L by dou W1. Okay. So to the first term, can you apply? Yeah, can you apply the derivative to this and tell me what happens? Just take your derivative inside and apply it to log. What is the derivative of log? What? Log of this function. Or else you can just simplify this by keeping the negative term here and then apply your log. Sorry, apply your derivative. So this term can be written as minus of log. I just have in the denominator, I'm just keeping the minus and I'm writing my log term like this. So can you apply the derivative for this and tell me the output? See, I am applying the derivative for the first term, this first term. Second. Okay, so for the first term, when you apply the derivative, what happens? So, 1 plus e power Then the derivative will go inside. It becomes exponential. And the derivative again goes inside. It becomes xi. Is this fine? This derivative, did you get this? Just applying derivative to your log and then applying to the inside function and then apply to your linear term. Okay, so did you get the same if you do the derivative? So this thing can be written as how can you write this? Okay, maybe let's just keep this term like this. What happened? What? Did I miss anything? Oh, okay. Here I'll have a minus. Okay, thank you. Okay, so then can you do it for second term? Second term is this. Okay, second term is this. Log of 1 minus pi, right? 1 minus 1 plus e power minus. Please be quiet. Okay, so this is your second term. Just apply derivative for this with respect to your 2w1. Can you do this and tell me what is the output? Again, here you have two terms. So here you will get, please be quiet. Plus, see, just split these two terms. Okay, sorry, here you'll have minus. Just split these two terms, then you will have yi into log of 1 minus yes, so now apply derivative for these two terms. What happened to this expression inside log? Can you simplify the expression inside log and then take your derivative inside the summation? Do you want to do it now or? Okay, you can do one thing. You can take this as your take home and do the derivative. It is very simple. You just have to take your derivative inside and do the derivative. So I'll just tell. So this is for the second term, no? Second term and first term, if you do, actually you will end up getting an expression like this. I think it is y minus pi and xi. Something like this you will get a simplified expression for your derivative. Okay, derivative with respect to w1, you will get a simplified expression like this where your pi is your predicted one. So using this you can easily implement your gradient descent for your logistic regression. Okay. Fine. So this is for one dimension, and your dou L by dou W naught also. I think you will not have your xi term, you will get something like this. Okay, so expression like this, maybe I'll just show you the end results. Yeah. So this is the results that you will get for your W1, and this is the result for your W0. Okay. So these two derivatives if you have, you can use your simple gradient ascent, no? Because I am trying to derive it for positive one. If you try to derive it for negative one, just use gradient descent and then you can learn your logistic regression. Okay, logistic regression for a simple one-dimensional data and for a simple binary classification. Now if you have k-class classifier and then a d-dimensional data, then how will the gradients change? Okay, so that we'll see. Yeah, for your d-dimensional case, you don't have simply W1 and W0 and W1, no? If you have a d-dimensional data, you will have W0 till some WD. Something like this you will have, right? But weight values. So you need to compute your derivative with respect to each of these terms. Okay, so for each of these term, if you actually expand your logistic regression framework, you will end up getting this as your derivative. Okay, so this as your derivative, where in place of xi you have the jth component of xi, because you are deriving with jth weight. Okay, so these things if you want it clearly, I'll again derive, but I don't think even if I set up the derivation, I may not finish. So we'll just take attendance and you can leave. See, for today, just just know the framework for your logistic regression, and it is maximizing your likelihood. And if we actually go into the deeper math, it is equivalent to minimizing your cross entropy. Okay. Just a minute. Do you? No, you can come and take, no? No, but I don't think I have it in. I don't have it in my iPad. I didn't download. You can connect, no?
Yeah. But this is type C.
Oh.
You need internet.
Huh?
Internet.
Internet I don't have. I don't have mobile.